Hi, and welcome to the Chapter 2 lecture in Gen Chem. I'm sorry I'm not going to be including my beautiful face in this lecture. It was just one too many steps, so you'll have to come to class to see me. So Chapter 2 is all about really atoms and molecules and ions, and these are all really particles that matter is made of. And so before we talk about the atom, we're going to have a little bit of a history lesson because it's really kind of an interesting story. How did we come to know of the atom and know that matter is in fact particulate and made up of small particles? So the first person known to sort of have a theory, or I shouldn't even say a theory, a hypothesis about what things were made of was Democritus, and he was a Greek philosopher, not scientist. And he had this idea that everything was made of tiny indivisible particles, that if you took, a stone and you cut it up and cut it up and cut up, that at some point you'd get to a tiny particle that could not be cut any further. And so he gave these particles a name. He called them atomos, which in Greek means uncuttable, can't be cut. I'll put uncuttable, even though I think that's a made-up word. Atomos, that's an O. The reigning idea, though, in Greece at the time, and really for about 2,000 years afterwards, was from the philosopher Aristotle, who said that all matter was composed of 4 elements: earth, wind, fire, and water. And that was really the reigning theory for a very long time. In comes John Dalton. John Dalton, who happened to like Democritus's theory that matter was composed of particles. And John Dalton was a scientist, and so this was no longer just philosophical thinking and meandering. This was testable and based on evidence. So John Dalton proposed his atomic theory that all matter is composed of small fundamental particles called atoms. He kept that name, the Greek name. That all atoms of the same element are identical in mass and properties. That atoms of different elements have different properties. And that atoms can combine to form compounds in whole number ratios. So John Dalton's atomic theory was not just thought up, it was based on known science at the time. So one of the first science laws that this was based on was something called the law of constant composition. The law of constant composition. So it was known in chemists studying chemicals that if you took a compound and you broke it up into its component elements, you always, no matter how much of that compound you had, you always got the same ratio of elements. So for example, if you took water and you broke it down into oxygen and hydrogen, you'd always have 1 oxygen for every 2 hydrogens. You'd have twice as much hydrogen as you did oxygen, always. So that means that water is always composed of 1 oxygen and 2 hydrogens. Another thing that John Dalton's theory included was that atoms are neither created nor destroyed during a chemical reaction. They can only be rearranged. And this is based on another law called the law of conservation of matter, sometimes called law of conservation of matter or of mass. Matter has mass, okay? So in other words, multiple experiments had shown that when you start with some mass of reactants, all right, that always is going to equal the mass of the products. In other words, matter can't be created or destroyed. You can't lose mass or gain mass out of nowhere. So when a reaction is run in a vessel, a sealed vessel, you can't lose mass or gain mass. So the way Dalton thought of atoms was as like tiny little marbles. He thought of them as like these solid little spheres that were the basic unit of matter. But as time went on, others started to wonder if perhaps atoms were made up of even smaller particles. In comes J.J. Thomson. And J.J. Thomson, with no P. By the way, you do not need to know the years of this. I put it on there for context. So this is, John Dalton was the early 1800s and J.J. Thomson was the late 1800s, meaning we've really only known about atomic structure, or really been thinking seriously about it for about 200 years, which is not that long in the span of things. I do want you to remember the names here. You will potentially be tested on the names of these people and their important roles in the history of the discovery of the atom. So you should know what they are associated with. So J.J. Thomson's big contribution was a set of experiments using cathode rays. Cathode ray experiments. So a cathode ray tube, it's a sealed like glass tube that has a vacuum in it or a near vacuum in it. And electricity is sent through the tube and through a tiny hole. And then electricity, which we now know are electrons, but they didn't know that yet, is shot through this little hole in the tube and creates a ray, right, that can be detected by a detector at the end of the tube. So here's what a cathode ray tube looks like. Here's the cathode and here's the anode, and electricity is run through from the cathode to the anode, and there's a little hole in the anode that the electricity shoots out, forming this straight line from the hole to the detector over here. Okay, so that's what happens normally. A little bit before we talk about these experiments about properties of electrical charge that hopefully are something you already know, but just to remind you, when it comes to electrical charges, opposites attract, like the Paula Abdul song says. All right, so I like to say positive loves negative, right? Opposites attract. And then sort of the complement to that is that like charges repel. Like charges repel. So positive and positives will repel each other. All right, and then the third rule of electrical charge is that opposite charges will sum zero. Meaning that if you have something that's positively charged and something that's negatively charged, overall those charges add together to equal zero. So it's a zero. Okay? All right, so now moving back to those cathode ray tube experiments. So normally when it's just the cathode ray tube, that beam travels straight, all right? But he did some other experiments and he put a magnetic field. So he used a magnet. Here's my little picture of a magnet. And when he used the magnet, it bent the beam. The beam bent either towards or away from the magnet. So that was evidence that the beam actually contained charged particles. So then, to determine what the charge of the particles were, he used some electrically charged plates, okay, and the beam always curved towards the positive plate. Since opposite charges attract, that means that the beam must contain negatively charged particles. All right, so this was basically the discovery of electrons. They were the first subatomic particle to be discovered. That matter is, although it appears neutral, is actually made up of charged particles. So electrons, which we can abbreviate with a little e and a minus sign. Okay, so now we know that there's some negatively charged particles. Next person who came in, and to still sort of work with these electrons was Millikan. Robert Millikan. And Robert Millikan did these experiments using oil drops. We're going to call it oil drop experiments. So what he did essentially is he used this contraption where he was able to spray a fine mist of oil particles, like you might use like a PAM or something to spray oil, and into and he also used X-rays to make those oil particles coated with charge and positive charge. So then he would drop these oil particles between two plates that were positively and negatively charged. And he, by controlling the amount of electricity he ran through those plates, he could slow the drop of the oil, or he could even levitate the oil droplet. And so by doing that, he was able to calculate the charge of the electron, what the charge of the electron is. So he was able to calculate the charge and also the mass of individual electrons through collecting data through these experiments. He realized electrons are quite small. They're actually 1,000th the mass of a hydrogen atom. So very, very small, but definitely negatively charged. And so by the rules of charge that we went over, if atoms have a negative charged particle, but they are neutral overall, then they must have a positively charged particle in there too to cancel out that negative charge. So we found electrons. Now the hunt is on for what we will learn are protons. But at the time, in the early 1900s, they just, philosophized that there was this positively charged material, but they had no idea whether it was particles, what kind of material it was. So the two reigning ideas of the time were of Nagaoka, who had he proposed a Saturn model, all right, where he said that there was this sort of sphere of positive charge, and then it was surrounded by a halo of negative charge. Versus Thomson, J.J. Thomson of the cathode ray tube experiments, who proposed what was called the Plum pudding model. Plum pudding. Now, plum pudding is like a British dessert. It's like a bread pudding with raisins in it. But maybe a more Americanized or modernized analogy would be like a bowl of oatmeal with raisins in it, or an oatmeal cookie with raisins in it. Basically, his concept was that the electrons were the raisins that were these, particles, and they were embedded within this sort of mesh of positive charge, which is the oatmeal or pudding part. All right. So between the two of them, again, we're now in the era of science and actually testing these hypotheses. And so Rutherford comes along and is able to do an experiment to test this hypothesis. So in 1911, Rutherford conducted his famous gold foil experiments. All right, now I should sort of preface this with Thomson's model was the one that was sort of reigning at the time. A model, by the way, is a term that's used in science when you have an idea about something and you sort of propose it based on not a lot of evidence, but that would fit the bill. And then you'd have to test that model to see if it was actually true. All right, so in Rutherford's gold foil experiment, I'm going to have to play around with some colors here. All right, what he did is he took some radioactive material, all right, that could shoot out these radioactive particles called alpha particles, right? And alpha particles are positively charged, okay? And then over here, he had a piece of gold foil, so a very thin sheet of gold, all right, gold metal. And then he had a detector screen surrounding it. So here's the detector. Nope, I want my detector to be gray. Erase that. And gray, okay. All right, so that's just like a film that will detect when the alpha particles hit it. All right, so I'm going to draw two of these. I'm going to duplicate this and show you. Oops. You can draw yourself two of these as well. All right, so here we have our box of radioactive substance, and there's a hole in it, and out of the hole is shooting these alpha particles at a piece of gold foil, and there's a detector screen to pick up that can detect those alpha particles when they hit. Okay, so if J.J. Thomson's model over here is correct, and we in fact have a plum pudding model where there's negative charged electrons just sort of meshed in with all this positive charge, then we would expect the rays, those alpha particles, to just kind of go through with very minimal deflection, all right, because the charge is all evenly dispersed. So the prediction, if Thomson's model was correct, was that the rays would go through something like this, maybe with a little bit of deflection, but they'd pretty much all be found on this part of the screen here, all right? If the Saturn model was correct, what would happen is the rays would go through in all the negative space, but if they hit that positively charged center, all right, they would bounce off because the alpha particles are positively charged and like charges repel. And so if that was the case, then the results would be that some of the alpha particles would go straight through the foil, some of them would deflect a little bit, and some of them might deflect a lot and actually bounce almost all the way back. And so what they found was that, or what Rutherford found was that this was actually what happened, that most of the rays of the alpha particles went through, so most of everything went straight through, but occasionally you'd have one that would bounce quite a bit. And this was actually really surprising, and Rutherford even quoted something along the lines of, it was like firing a pistol at a piece of tissue paper and having the bullet come flying back at you. It was that much of a surprise to them. But it really did establish the fact, that sort of planetary model of the atom, that in fact the Saturn model was more correct. And so the things that Rutherford's gold foil experiments established are that the volume of the atom is actually mostly empty space. that those alpha particles could flow through. It's mostly empty space, as you can see in this picture here. Also, that there must be a relatively small but heavy, positively charged body in the center, which we call the nucleus. Nucleus just really means center. And then he did some other experiments and actually figured out what the mass of these positively charged particles were. And they named them. And the name of these particles are protons. Positively charged particles. And sometimes we'll just abbreviate that with a P plus for proton. Okay, so now we've discovered electrons and we've discovered protons. All right, but what was also known is that although Rutherford figured out the mass of the protons, he also realized that protons didn't account for the entire mass of the atom. And then a couple of more important discoveries came together to really give us a better picture. In 1913, which was just a couple years after Rutherford's gold foil experiments, a different researcher named Soddy recognized that an element could have atoms with different masses, but still have the same chemical properties. So like carbon, for example, you could have different atoms of carbon that had different masses, but still all behaved just like carbon. We call these different versions of an element isotopes. And we'll talk more about isotopes, but just the discovery of them led to this concept still that there was a mass element in the atom that had not been accounted for. So it took a while to find that particle because it's a lot easier to find particles with charges, right? Because you can do experiments where you look for charged particles, but it was a lot harder to find these non-charged parts. And these non-charged parts that also reside in the nucleus with the protons are called neutrons. And they were discovered in 1932 by a Dr. Chadwick, and that sort of completed the picture that we have of sort of the atom as it stands now. Now, I should say physicists since then have discovered even smaller particles, and that really gets into nuclear physics. That's a level that we don't get to in general chemistry. So the parts of the atom that we will discuss, sorry for all the random lines there, are protons, neutrons, and electrons. These are the most important major subatomic particles. So we have electrons, which we can represent with an E minus, protons, which are often represented as P plus, and neutrons, which are represented as an N or sometimes an N naught, with a little zero there. Because electrons have a negative charge, protons have a positive charge, and neutrons have zero charge. Their masses have all been calculated as well. Notice that protons and neutrons have nearly identical masses. Both of them weigh almost exactly 1 atomic mass unit. They are both found in the nucleus, that tightly packed dense center of the atom, and electrons fly around the cloud. So our current picture of an atom is, let's say if we color-coded this, so protons we'll say are blue in the nucleus, and neutrons are red in the nucleus, and then we have electrons that fly around outside, and that space that they fly around in is sort of known as this cloud. And we could even color in that cloud. So most of the space of an atom is actually empty space. I'm kind of skipping around here, all right? I'm going to skip down to this modern atomic theory. So I've drawn the picture up here of our modern day atom, that an atom consists of small, dense, positively charged nucleus here that's surrounded by fast-moving electrons. Almost 100% of the mass of the atom is in the nucleus, because really most of the mass comes from protons and neutrons. Electrons have a fraction of the mass of those two particles. But almost 100% of the volume of the atom is actually made by the electron cloud. And the electron cloud is actually mostly empty space. There's electrons, a handful of electrons flying around in this massive space. A really good analogy that I heard once was if you took an atom and you visualized it the size of a football stadium. All right, so the football stadium represents the cloud. The nucleus would be represented by a grapefruit in the center of the stadium. That's how small the nucleus is relative to the cloud. And the electrons would be like a handful of blueberries flying around the stadium. So again, an atom, mostly empty space, which is kind of crazy to think about. This whole world, all the solid things around you are actually mostly empty space. Atoms are, by definition, electrically neutral, meaning that the number of protons equals the number of electrons. I wrote that funny, but you might write it better. The number of protons equals the number of electrons. That makes them neutral. And that atoms of the same element have the same number of protons. It's the protons that determine the actual identity of the element. So the part I kind of skipped over up here, is about the weight units or mass units that we use to measure atoms and their subatomic particles. Grams are just too big. And so we created a new unit called the atomic mass unit, or AMU. And an AMU is defined as exactly 1/12 the mass of a carbon atom. And so if we wanted to do a conversion to grams, 1 AMU is 1.66054 times 10 to the 4th grams, or 1 gram is 6.02 times 10 to the 23rd AMUs. This number, you might want to take a little mental image of. You're going to see it again very soon. Okay, so as I left off saying with modern atomic theory, protons, the number of protons that an atom has defines what element it is. All elements that have 20 protons are the same, or all atoms of 20 protons are of the same element. So it's the number of protons that determines the elements. Now, when it comes to elements, we can find these on our periodic table. There are 118 different known elements on planet Earth. 90 of those, by the way, they occur naturally, but the rest of them are actually man-made. They've been made in a lab by bombarding atoms together and fusing them together. Some of them have only existed for like a millisecond inside a machine. So, I don't know the importance of some of those higher number ones, like 116, since it only existed for a millisecond. But it's a relatively small number of elements that make up the entire world. So every element has its own unique symbol on the periodic table and a name. And the symbols are universal. So no matter what country you're in, PB is lead and C is carbon. All right, but the names are slightly different in different languages. The classic one is aluminum. Aluminum is how we say it in the US, but in British English, it's pronounced aluminium. So that's not a mispronunciation, it's an actual difference in pronunciation. So Al is the symbol for aluminum. Symbols are either 1 letter or two letters. And if there are two letters, then the first is capitalized and the second is lowercase. And that may seem like a small detail, but it's actually a very important detail. Because, for example, Cu with capital C lowercase u, that is the element symbol for copper. But if you wrote Cu, both uppercased, okay, that C, a capital C is carbon, and a capital U is uranium. So this is not an element. This would represent a compound made of carbon and uranium. So those punctuation details, whether something's capitalized or lowercased, is actually really important and something to pay attention to. And you would get points off if you didn't do it correctly. All right, so about the elements in the periodic table, some important numbers to know. The first is called the atomic number. Atomic number. And the abbreviation for the atomic number, I don't know why, is Z. Okay? And what the atomic number is, you'll find it at the top of the periodic table. And it represents the number of protons in an atom of that element. So the atomic number on top, if you pull out a periodic table right now, look at any, let's say look at carbon. All right, carbon, the number above it is 6. That means that every carbon atom has 6 protons. And any atom on the planet that has 6 protons is therefore an atom of carbon. Another number to know that's important for atoms is the mass number. All right, the mass number is represented by the letter A. Again, I have no idea why A is the abbreviation for that. And it is the number of protons plus the number of neutrons. All right, it is a whole number. It's not found on the periodic table, the mass number. You get it from adding together the number of protons and neutrons that an atom contains. And if you want to figure out how many neutrons the atom contains and you have the mass number, it's just a little subtraction problem. The mass number minus the proton number tells us the number of neutrons. All right, so this little thing right here is a handy-dandy little cheat sheet for you when you're working some of these problems that you're going to be working in the homework to determine numbers of protons, neutrons, and electrons that different atoms have. So remember, atoms are electrically neutral by definition, which means that the number of protons, which are positively charged, must equal the number of electrons, which are negatively charged, so that those charges cancel out, right? But you can actually have particles that have different numbers of protons and electrons and are charged. But we don't call those atoms. We call them ions. All right, so atoms are neutral, ions are charged. And so they're charged because the number of protons and the number of electrons, in this case, are not equal. Okay? So negatively charged ions, we call those anions. And positively charged ions are called cations. All right, and a funny mnemonic that I've heard throughout the years to remember that cations are positively charged is that cats have paws. All right, positively charged, cat paws. And you can figure out what the charge is, the magnitude of the charge, simply by doing a little math problem, figuring out, taking the protons and subtracting the number of electrons. All right, and if you have the same number of protons as electrons, that subtraction will come out to 0. You have a neutrally charged atom. But if the number of protons and electrons differ, then the what is it called? The answer to the difference of that subtraction problem will be the charge of the atom. So let's do some example problems. Let's pretend we have a sodium atom with a mass number of 21. It has a neutral charge, and we want to know how many protons, neutrons, and electrons it has. All right, so we know that it's sodium. The first thing we should do is find sodium. We need to find the number of protons. We need to find Z on the periodic table. So we look on our periodic table, we look for sodium. Sodium is Na. That's because it was originally named in Latin as natrium, and then we changed it at some point. So we kept the symbol, but we changed the name. Okay, we found it on our periodic table. It is number 11, and so that means the Z, or the number of protons, is 11. Now, we know it's a neutral atom. Since it's neutral, the number of protons equals the number of electrons. So the number of electrons here must also be 11. All right, and now to figure out the mass number, A, we use that equation to figure out the neutrons, we need to use the mass number. So A minus Z, or in other words, the mass number minus the number of protons. So it says in the problem the mass number, A, is 21, and we figured out that they have 11 protons. So the number of neutrons is 21 minus 11, which is 10 neutrons. Okay, so we just use these rules here, and these rules here, I guess, as well, to identify how many protons, neutrons, and electrons. And let's pretend this one is not an atom, but an ion. If the sodium atom above had a 1 plus charge, how many electrons does it have? All right, so remember, it's the number of protons minus the number of electrons gives you the charge. So if it has 11 protons, and how many electrons would it have in order to have a plus 1 charge? All right, so 11 minus what equals plus 1? X equals, in this case, 10. So it would be 10 electrons. If it had a 1 plus charge, it means it has 11 protons and 10 electrons, which makes sense. Protons are positively charged, so if it has a positive charge, it needs to have more protons than electrons. Okay, so there will be plenty of practice problems on that. It's simple math, just basically addition, subtraction, and looking on the periodic table. But practice makes perfect, and you'll also be doing a little lab on this as well to reinforce it. But now we're going to come back to a concept that I mentioned earlier. Remember, we talked about Soddy and his discovery of atoms of the same element with different masses but same properties that we called isotopes. Isotope, iso, means same. And the name isotope basically means that they're in the same place on the periodic table. So they are atoms that of the same element, meaning they have the same number of protons, but they have different masses. And the reason, now we know the reason that they have different masses is because they have different numbers of neutrons. All right, but I'll reinforce, but they have the same number of protons. All right, protons define the element. If they had different numbers of protons, they would not be the same element. So we're going to talk about isotopes and different ways to represent them, or to represent atoms in general. So we often will see atoms represented in something called symbolic notation, where X represents the chemical symbol from the periodic table, so like Na for sodium or Mg for magnesium. And then the mass number is on the top left as a superscript, and the atomic number is on the bottom left as a subscript. Another way to represent them is just to say the element name element name with a dash and the mass number. So for example, we have different isotopes of carbon. So there is carbon 12, but all elements of carbon have 6 protons. All right, there's carbon 13, but it still has a 6 as its mass number. And there's also carbon 14. Do I have room for this? Carbon 14. So these are 3 isotopes of carbon. Carbon 12, so we can also call this one carbon 12. This one is called carbon 13, and this one is called carbon 14. All right, so carbon 12 has 6 protons, 6 electrons, and 6 neutrons, because 6 protons plus 6 neutrons gives us that mass number of 12. Carbon 13 has 6 protons and 6 electrons, but it has a higher mass because it has an extra neutron. And likewise, carbon 14 has 6 protons and 6 electrons, but the different thing about it is that it has 8 neutrons, because 8 plus 6 equals 14 for that mass number. Okay, so these are isotopes, different, I like to say like different flavors of the same element. Alrighty, so there might be some questions asking you about different isotopes and how many protons, neutrons, and electrons they have, and or how to write things in symbolic notation. So those are going to be things that you're going to practice until you become proficient with. Okay? But if you were paying attention and had your periodic table handy when we were talking about mass number and atomic number, you notice that there is another number on the periodic table for each element that we didn't talk about, the one underneath it. And that does have to do with the mass of an element. We call it the atomic mass. All right? And the atomic mass is an average. All right, so for carbon, for example, we said there are 3 different isotopes of carbon. All right, and if you look at the periodic table for carbon, all right, the atomic mass on the periodic table for carbon is 12.01 or 12.011, depending on the periodic table you're looking at. So it's not exactly 12, and it's not an average of 12, 13, and 14. It's a weighted average, okay? So it's actually an average mass of all of the isotopes based on their percent abundance of each isotope, okay? So the fact that there are 3 isotopes of carbon, and they weigh 12, 13, and 14 respectively, but the fact that the average atomic mass is so close to 12 means that carbon 12 is by far the most abundant isotope of carbon, with carbon 13 and carbon 14 making up very small percentages. And so how to calculate a weighted average is you use the fractional abundance, or you take that percent abundance and you turn it into a fractional abundance. So you take that percent and you convert it to a decimal to use in your calculations. So the average mass, which is the atomic mass that's on the periodic table, is calculated by multiplying the abundance of the isotope times that isotope's mass, and then adding it. So this is a symbol for sum. So you're taking the sum of all of the isotopes times their proportional abundance. All right, so let's do an example problem and show you how magnesium is calculated. So there are these machines called mass spectrometers, and you can take a sample of magnesium and put it in there, and it'll break it down into the different isotopes and give you a readout. What percent is isotope 24, 25, 26. And also can tell you the exact mass of each. So magnesium 24, the percent abundance is 78.99%, And the actual mass is not 24, but 23.985, which rounds to 24. All right, so when we do this calculation, we're going to figure out the atomic mass, which is an average. Sometimes I just call it the average atomic mass, just to clarify that. So we need to take the percent of magnesium-24 times its mass, the abundance of magnesium-25 times its mass, and the abundance of magnesium-26 times its mass. But we just convert these percentages into fractions, basically divide them by 100. So we get, for the first isotope for magnesium-24, 0.7899 times 23.985, plus the abundance times the mass of magnesium-25, plus the abundance times the mass of magnesium-26. So this is a multi-step problem. The first thing we want to do is multiply. I ordered that wrong, but whatever, multiply. Okay, so this problem here, the answer is 18.94575 according to my calculator. Okay, but this number that we measured, this percentage, has 4 sig figs. So I'm just going to put a little placeholder here. That 4 is the last significant figure in that number. And then we've got the product of this, 2.4986. And again, it's going to be 4 sig figs. So I'm going to put my little placeholder under the 8, plus the product of this, 2.86072, says my calculator. And again, this number has 4 sig figs, this one has 5. So this is significant 4 places out, because these are multiplication problems. But now the second thing we need to do is addition. And remember, when we do addition, the rules for sig figs are different. So I'm just going to add all these together, and I get 24.305078. All right, but now I need to figure out where to round that to. All right, so each of these numbers has 4 significant figures in the multiplication line. All right, but we don't keep the same number of sig figs per se when we're doing addition and subtraction. It's only significant to the last significant place. So this one is significant 3 places past the decimal point, 3 places past the decimal point, and 2 places past the decimal point. So it's significant to the least number of places past the decimal point, so 2 places past the decimal point, which ends up being 4 sig figs, so even if you went with the wrong rules, you'd still get the right answer. 24.30 AMU. And you should be able to match that on your periodic table. That should be what the periodic table says. It should match. All right, so when you do these problems, you should be able to check your answer is correct by checking the periodic table. On a test, so on like your homework, I might give you problems with real isotopes and real elements that you can then check on your answer on the periodic table. But on a test, I would give you a made-up element with made-up isotopes. So you would have to actually know how to do the math, and you would not have a periodic table to check it on. So do make sure you practice some of these problems and know how to calculate the average atomic mass. All right, here's another type of question, more conceptual than mathematical. So we have 2 isotopes. Well, actually, first, let me point out in this problem that we just did, another way to check ourselves, okay, is we've got an average mass of 24.3, which is very close to 24, all right, which makes sense because isotope 24 is the most abundant. So in a weighted average, the average will be very close to whichever one is most abundant. So a more simple question here, boron has 2 isotopes, boron 10 and boron 11. Based on the atomic mass on the periodic table, which is more abundant? Well, if we look at the periodic table, the atomic mass of boron is 10.81, all right? Is 10.81 closer to 10 or 11? Well, that number is closer to 11, which tells us that boron 11 is going to be the more abundant of the two isotopes because the average is weighted towards the side of 11. All right, another thing to know, when we combine atoms to make compounds, those compounds, we can express them using a formula. So this here is an example of the formula for glucose, C6H12O6. And we call this the molecular formula. Molecular formula. So it uses chemical symbols like C, H, and O, and subscripts, these little 6, 12, and 6, that indicates the types of atoms and number of each type in the atom. So in other words, glucose has 6 carbons. That little 6 attached to the C is 6 carbons. It has 12 hydrogens, and it has 6 oxygens. All right, every molecule of glucose has that same composition. A way we could sort of simplify that, so like in math, when you have fractions, you're often told to simplify them to the simplest form. We can do that with molecular formulas too. And we call that the empirical formula. Empirical formula. And the empirical formula indicates the types of atoms in their simplest whole number ratio. So glucose, we could divide all of those subscripts by 6 and simplify this to 1 C, 2 hydrogens, and 1 oxygen. So this would be the empirical formula for glucose. It's not the actual formula for glucose. If you just had 1 C, 2 H's, and 1 O, you could not make a glucose molecule. But if you have multiples of that, you can get glucose. So you need, at least if you're trying to make glucose, you need 1 C and 1 O for every 2 H's. It's sort of just a ratio of the different elements that you need. So here's a quick example problem. A molecule of metaldehyde, which is a pesticide that's used for snails and slugs, contains 8 carbon atoms, 16 hydrogen atoms, and 4 oxygen atoms. What are the molecular and empirical formulas? So the molecular formula, it basically told us in words, and we're just writing it out in symbols. It has 8 carbon atoms, so we put C, the subscript of 8, 16 hydrogen atoms, H, the subscript of 16, and 4 oxygen atoms. All right, the empirical formula would be if we simplify that. All right, so we divide by some number to get the simplest ratio. So we can't divide by 8, we could divide by 4 though. So if we divide them all by 4, then 8 divided by 4 is 2, 16 divided by 4 is 4, and 4 divided by 4 is 1. So the empirical formula here would be C2H4O. So there will be some problems for you to practice writing molecular formulas and empirical formulas. And later in the class, we'll learn how to determine empirical and molecular formulas from actual experimental data, which is how early scientists actually determined the makeup, the chemical makeup and the chemical formulas for different compounds. All right, and then the last big thing in this chapter with math is all about the mole. So the mole is a funny word, and we're not talking about the little creature that digs holes in the ground. All right, this is actually a number. Kind of like a dozen is a number. A dozen means 12. The mole is also a number. So we, in chemistry, use the mole. It happens to be a really, really large number, and we can abbreviate it as MOL. So a dozen is 12. All right, a mole is 6.022 times 10 to the 23rd. 6.022 times 10 to the 23rd. All right, it's huge, huge, huge number. And it was determined by a scientist named Avogadro. Avogadro, so we call it Avogadro's number. And an abbreviation for that is N sub A, Avogadro's number, or the mole. So this number, you may, if you flip back in the pages of the notes, this is how many atomic mass units is in 1 gram. And that's going to become relevant in a moment because it's going to be how we convert the number of atoms to grams of atoms, or the mass of atoms in atomic units to the mass of atoms in grams. Anyway, 1 mole of anything is 6.022 times 10 to the 23rd. So if you have a mole of carbon atoms, 6.022 to the 23rd atoms. If you have a mole of water molecules, 6.022 times 10 to the 23rd molecules. If you had a mole of pennies, that's 6.022 times 10 to the 23rd pennies. FYI, a mole of water molecules is about a shot glass full of water. 18 milliliters is a mole of water, versus a mole of pennies is actually enough to give every person on Earth, $1 trillion in pennies. Though it would be hard to spend that money because we'd also be buried in pennies 400 meters deep across the face of the planet. So huge number to conceptualize. And also just kind of goes to show how tiny atoms are. They're so small that we have to use such a huge number to even really talk about them. So when we are doing calculations with Avogadro's number, we can basically, it's an equivalency that we can turn into a conversion factor that we can use to convert between number of particles of something and moles. So we can make that equivalency into one of 2 conversion factors or ratios, and we can do some math. So let's practice some problems here. Example question. How many atoms are in 4.38 moles of gold? So we take what we're given in the problem. It's asked, gives us 4.38 moles, and we need to convert it to atoms. And the conversion between moles and atoms is, of course, Avogadro's number. So we're going to multiply it by a conversion factor, where we have atoms on the bottom. Oops, just kidding. Where we have moles on the bottom, because we have moles up here and moles up here, and we want them to cancel out. And then we'll have atoms on top. So 1 mole is 6.022 times 10 to the 23rd atoms. Our moles cancel out, and our answer will be in atoms. So 4.38 times 6.022 times 10 to the 23rd comes out, and we convert the answer to correct scientific notation, and we get 2.64 times 10 to the 24 atoms. And notice that my answer, the number that I'm given in the problem here, is 3 sig figs. So I want my answer to be 3 sig figs as well. Okay. Problem number 2. How many moles is 9.15 times 10 to the 22 atoms of zinc? 9.15 times 10 to the 22 atoms. And now I want to flip that conversion factor because I want atoms on bottom and moles on top. So my atoms will cancel out. 6.022 times 10 to the 23rd atoms. And so this is a division problem now. 9.15 times 10 to the 22nd divided by 6.022 times 10 to the 23rd. And the answer is 0.152 moles. Remember, answers in chemistry always need to contain a number and a unit. A number and a unit. It is not complete without the unit. Though you'll notice on some of your quizzes, in order to make sure you got the right number, I couldn't have you type in a unit. So I always say explicitly, just type in the number value, not the unit, to even remind you that your answer should actually contain a unit, but in this special circumstance, I'm letting you only contain a number. But on tests and every other scenario, your answer should contain a number and a unit. This is a good problem. These are some good problems to make sure that you understand how to correctly type scientific notation into your calculator or to do calculations with scientific notation. So if you're not doing the problem along with the lecture, you might want to pause it here and just type this into your calculator and make sure that you get those answers. Because if you don't, then that's something you need to figure out between you and your calculator, and I can help you, but it's a number you can use to check. All right, so when it comes to, again, elements and substances made of atoms, one atom is such a small amount of something that moles are really more workable amounts of atoms and compounds. And so we have this measurement called the molar mass, or it's represented by a capital M, or sometimes by two capital M's, molar mass. All right, and it's the mass of 1 mole of a substance. And the units, therefore, of molar mass are going to be grams per mole. All right, for elements, the molar mass is numerically the same as the atomic mass. All right, from the periodic table. So for example, 1 atom of copper, according to the periodic table, is 63.55 AMUs. So 1 mole of copper is 63.55 grams. So 1 atom is 1 atomic mass unit, and 1 mole is the same number but in grams. So it makes it really easy. We can use the periodic table basically to find the molar mass of any element. We just convert that atomic mass from AMUs to grams. Yay! For compounds, the molar mass is the same as the formula mass. Now the formula mass is just the sum of all the masses of all the atoms in the chemical formula. So for example, with water, H2O is 2 hydrogens and 1 oxygen. So we take the mass of 2 hydrogen, so 2 times the mass of hydrogen, plus 1 times the mass of oxygen, and the formula mass for water is 18.01 atomic mass units. And we can calculate that using our periodic table and doing a little multiplication and addition, basically. So for any compound, you can figure out the formula mass using the periodic table and adding the masses of all of those atoms together. So if 1 molecule of H2O is 18.01 atomic mass units, then 1 mole of water is just 18.01 grams. Okay, so molar mass, pretty easy to calculate, but then it's also really useful because molar mass is, of course, in grams per mole. And so, for example, we can convert those equivalencies into conversion factors. So for copper, we said it's 63.55 grams in 1 mole of copper, or we can reverse that, okay? So we can use it in calculations to change between or convert between mass and moles of something. So for example, what is the mass of 0.825 moles of iron? So the first thing we want to do is figure out the molar mass, because we're going to need that to make our conversion factor. So what is the molar mass of iron? All right, and we go to the periodic table and we find that 1 mole of iron is 55.85 grams. All right, or in other words, we could say that iron has a molar mass of 55.85 grams per mole. Okay, either way. And now we can use that conversion factor in this problem. So we take what we're given, we start with that number we're given, 8.25 moles, and now we want to cancel out the moles. So we want moles on bottom, grams on top, and as this says, it's 55.85 grams per 1 mole. All right, we assume the number that we get from the periodic table is significant. We'll always use a periodic table that has numbers that are significant out, 4 or 5 significant figures. In this case, our given number has only 3 sig figs, so that is determining the sig figs of our answer. So our answer here, 8.25 times 55.85 is 461. That's 3 significant figures. Grams, a number and a unit, right? Our moles canceled out, which left us with grams. Next example problem. How many moles is 38.6 grams of lead? Well, first thing we need to know is the molar mass of lead. And the molar mass of lead according to the periodic table, and lead is Pb, by the way. It's where plumbing got its name from, because the Latin name for lead was plumium, and then we changed it. Okay, so if we look at the periodic table, we find lead, it's 207.2 grams per mole is the molar mass. So now we can actually do the problem. We have 38.6 moles of lead, and 1 mole of lead is 207 grams, or 207.2 grams. Cancel out our moles, and we do the math, and we get 0.18. That's too messy. 0.186 grams of lead. Okay. Now we have one that asks a slightly different question. It says, what is the mass of 5.58 moles of methane? So we have first thing we need to know is the molar mass of methane. All right, and it's a compound, so we have to do, there's 1 carbon. Carbon is 12.011 grams. And we add that to the mass of 4 hydrogens, grams per mole. And we get a molar mass of 16.042 grams per mole. That's the molar mass of methane. So now we can do this problem. We have 5.58 moles of methane, and we multiply it by the molar mass times 16.042 grams per mole equals 89.5 grams. Okay, because I had 3 sig figs in my given, so I need to have 3 sig figs in my answer. So I rounded it to 3 sig figs. All right, so one thing I am realizing now that I could have done, all of these problems, oh, no, I just did problem number 2 incorrectly. No wonder. Okay, so if you didn't catch it, I'll show you where I went wrong. The question said how many moles is 38.6 grams of lead, but in my problem I said 38.6 moles of lead. All right, so I need to redo that. I read it wrong, and I did it wrong. So my answer is actually correct because I copied that down. All right, so let's reset this up correctly. All right, I am human too. I make mistakes in my math, and I have to go back and correct them, so don't feel bad when it happens to you. So we were starting with is actually 38.6 grams of lead. All right, and we want to convert it into moles. So now we need our grams on the bottom and our moles on top. 1 mole is 207.2 grams. 38.6 divided by 207.2 is in fact 0.186 moles of lead. And perhaps you noticed before that my answer didn't really match up with my problem setup, because 38 times 207 is certainly not less than 1. But now we have done it correctly, okay? So notice that in these problems, sometimes you're going from mass to moles, sometimes you're going, or I guess you're going from moles to mass, sometimes you're going from mass to moles. Either way, you use that conversion factor. All right? So we've actually learned a lot of different things that can be used, a lot of different values that can be used as conversion factors. Density is a fraction, it's a mass per volume. Molar mass, which is grams per mole, and Avogadro's number, which is particles per mole, or moles per particle. Yeah, particles per mole. So we can use those as conversion factors to convert between different measurements. We can take, if we know the volume of something and the density of it, we can figure out its mass. If we know the mass and we want to know how many particles it consists of, we can do that too. We have to convert mass to moles, and then we can convert moles to particles. So this, I call this the unit conversion roadmap. And it kind of is a visual model. So if you have moles, but you're asked for volume, that means you're going to need to use the molar mass and the density in order to, as conversion factors in order to do that. Or if you're given the mass of something and it asks you how many particles you have, you can do that. It'll be 2 steps using the molar mass and Avogadro's number. So kind of getting used to this roadmap, finding kind of as a way to sort of figure out the steps that you need to take. But always keep in mind that with unit conversion, the key is getting your units to cancel out. Finding conversion factors that allow you to go from one unit to another until you're ultimately at the unit that you want. So let's do a couple of these multi-step problems here. So the first one, how many atoms are present in a 93-gram sample of magnesium? So the number we're starting with is 93. That's not 93. Let's try this again. 93.5 grams of magnesium. I like to write that so I know what I'm talking about. All right, so I need to, the only way that I can go from grams to something else, I could go to grams to volume using density. That doesn't make sense. So I'm going to go to grams to moles, and I can do that using the molar mass. I want grams down here and moles up here. So 1 mole of magnesium, if we just look at the periodic table, we find magnesium has a molar mass of 24.31 grams per mole. All right, so we've got grams canceling out, and now we need to cancel out moles. So I need something with moles on the bottom, and I want to know how many atoms. Do I have a conversion factor that relates moles and atoms? Why, yes, I do. It's Avogadro's number. 1 mole is 6.022 times 10 to the 23rd atoms. All right, so now my moles cancel out, and I will have gone from grams to atoms. So now I just need to do the math. 93.5 times 6.02 times 10 to the 23rd divided by 24.31. I always multiply the top and then divide by the bottom. And my answer needs to have 3 significant figures because that's what I'm given in my given number. So I type it all into my calculator and I get 2.32 times 10 to the 24th atoms. Okay, let's do another. Determine the mass, so I'm trying to get to grams generally, of 7.58 times 10 to the 21 molecules of benzene, C6H12. All right, so the first thing I want to do is just get that molar mass of benzene, C6H12, and that is going to be 6 carbons. Carbons are 12.011 grams per mole each, plus the mass of 12 hydrogens. So the molar mass of benzene is 84.18 grams per mole. All right, so now I can use that in my conversion problem. So step 2 is to actually do the conversion. So if I have 7.58 times 10 to the 21 molecules, I need to convert that to moles. So molecules per mole, or 1 mole is 6.022 times 10 to the 23rd molecules. My molecules will cancel. Next, I want to multiply it by something with moles on the bottom and grams on top, so I can convert it to grams. 1 mole of benzene is 84.18 grams. So now my moles cancel, and my answer will be a mass in grams. So when I type all this into my calculator, the answer I get is actually 1.06 grams. No, 1.06 grams. My key, I have it wrong. 1.06 grams of benzene. And one more practice problem. Maybe pause the video, see if you can do it yourself, and check. It says, how many molecules of water are in 5.50 milliliters of water? And it tells us the density of water is 1 gram per mil. So let's do this in that stepwise fashion. Let's write out all the equivalencies that we actually need. So we're given density, all right, is 1.00 grams per milliliter. All right, the molar mass of water, we actually calculated earlier in the lecture, so I'll just write it here, is 18.01 grams per mole. And of course, Avogadro's number, I'm not going to write that one out, but we might need to use that one as well, because it's asking how many molecules. So now let's actually set up and do the problem. We start with what we're given in the problem, 5.50 milliliters of water. If we want to cancel out those milliliters, the only thing we can turn them into, because the only conversion factor we have with milliliters is density. So we can use density to go from milliliters to grams. So our milliliters cancel. Now we can go from grams to moles, because we have a conversion factor to do that. So 1 mole is 18.01 grams. Our grams cancel. And then lastly, we can use Avogadro's number to go from moles to molecules. 1 mole is 6.022 times 10 to the 23rd molecules. So now we just have to do this math in our calculators. Multiply everything on top, divide by everything on bottom, and the answer we get to 3 sig figs, because that 5, 5, and that 0 there are all significant. Our answer in 3 sig figs is going to be 1.84 times 10 to the 23rd molecules. Ta-da! And if you remember what I said before, earlier in the lecture, that 1 mole of water is actually about 18 milliliters of water. This makes sense because 1.84 times 10 to the 23rd is not quite a mole. 6 times 10 to the 23rd is a mole. So yeah, it's about a fifth of a mole, and I guess, it's about a third of a mole. 1.84 is about a third of 6, which makes sense because 5.5 is about a third of 18. So it's always a good idea to like sort of common sense check your math answers and make sure they fit. That was an example where we could do that. And an example where I didn't do that was above when I did my calculation all wrong. And maybe you caught it. Hopefully you caught it. And luckily I did go back and I caught it myself. So that is the end of chapter 2. There's a lot of math to be practiced, a lot of unit conversion. So we're building on that unit conversion that you were practicing and learning in chapter 1. We're continuing to use it in chapter 2. In chemistry, we have to do these kinds of problems all the time. Convert from units using different conversion factors, which can be things like density and molar mass. So practice makes progress.